So show that the time required for a projectile to reach its highest point is equal to the time for it to return to its original height if air resistance is negligible. So first we would want to choose a couple things. We'll choose the origin to be the point of launch and upwards to be positive in the y direction. So we're dealing with height. So the initial velocity of the projectile is v naught. The launch angle is theta naught. Acceleration in the y direction equals to g, but up is positive, g is acting down, so g is going to be negative in this case. Our initial height, we're going to make our initial height 0. And we're not dealing with the range. We're not dealing with how far the ball goes or the projectile. We're analyzing this problem in the y direction. We have the velocity in component form, v naught cosine theta, v naught. We're not going to analyze this problem in terms of range. So at this point, we don't care about the x component of the velocity. We're dealing with height, so we're going to use the y component to analyze the problem. To find the time required to reach the highest point at which v in the y direction is going to be 0, we know that the final velocity here is going to be 0, and it's in the y direction. So to find the highest point that the projectile reach, we'll use this equation. Final in the y direction, initial in the y direction, times plus acceleration times time, and this time is going up. Solving for time, we get the final velocity in the y direction minus the initial velocity, y direction, over acceleration, which is negative g. The final velocity is going to equal to 0. Negative and negative is going to be positive. So time up is going to equal initial velocity sine theta naught over gravity. So that's a time to reach the highest point. Okay, now we would like to find the height at the highest point. In order to do that, we'll use this equation. Y max is at the highest point minus initial height. Solving for the max height, we know that the initial height is equal to 0. We know that the final velocity is also going to equal to 0. And we're dealing with the y component of the velocity. So that's the initial. And this is going to be over negative 2g. So the max height is equal to, so that's the max height. Now that we have the max height, we would like to use that to find the time for the object to fall the other part of the path with a starting y velocity of 0, because at this point here, velocity is going to equal to 0. And the starting height, because remember the height at that point is equal to that. Now we're dealing with this other half of the path. In order to solve that, we're going to use an equation that involves height and time. So we're going to have final height equals initial height plus the velocity in the y direction, and that's initial, times time, plus 1/2 acceleration, and that's in the y direction, times t squared. We know that the final height is going to equal to 0 because we're starting from a height here and we're going to this height, which is 0. We know that the time, so let's start it first. So we know the final height is going to equal to 0. We're starting from a height of b squared naught sine square theta naught over 2 times that of g plus the initial velocity at that point at the peak is going to equal to 0. So we have 0 times the time to go down. Well, that goes to 0. We know that the g is going to be negative. So that's 1/2 that of g, the time to go down, squared. So solving for t, get t squared equals plus or minus the initial velocity sine theta naught over g, and this is the time to go down. We choose time to be positive because we cannot have negative time, and that's the time to go down. So looking at the problem, show that the time required for the projectile to reach its highest point is equal to the time for it to return to its original height. So time to return to its original height. So the time it took to reach its highest point is the time up, and that's equal to the time it takes to reach its lowest point. So we have time up is equal to time down. That's it.